Hello, welcome to this video 8-3, and today we're going to recap the last two lessons graphing exponential growth and decay functions of base 2 and base 10, and go ahead and be able to just look at a function and identify, is it exponential growth or is it exponential decay. The prior knowledge that we have here, just to activate your memory, is it says rewrite the function with a base of 2. Well, remember, I can go ahead and I can change this base 1/2 to be a base of 2 if I utilize the negative exponent property. So here is the same function written as base 2. So 2 to the power of negative x, that's really base 1/2, but we can go ahead and rewrite it with a c value of -1 in order to be able to graph it with our key points from base 2, which we'll go ahead and look at in this lesson. Our objective today is to identify and graph exponential growth and decay functions. We're going to go ahead and identify exponential functions as growth or decay in this format. We have our a value, which is the coefficient, a multiplier out front. We have a base. That's always at least what we're going to look at today with graphing. It's going to be base 1/2 or base 2. Maybe even we'll throw in base 10 or base 1/10 if we have time. But that's your base, and it's attached to the exponent. If you have a negative or a coefficient out front in your exponent, that's what we call a c value. Remember, that affects our horizontal growth and our horizontal stretch and compression, as well as reflection. And then we have an h value, which is given here. That moves us left and right, as well as our k value moves us up and down, which is really tied to our horizontal asymptote. So what we're going to do today in order to identify growth or decay is we're going to consider the function when it is in the form where the coefficient of x is positive. It's very important that our coefficient of x is positive, so we're seeing the true base. If b, the base, is greater than 1. If it's greater than 1, then that is exponential growth. And think about this. Base 2. 2 times 2, that's 4. Times 2, that's 8. Times 2, that's 16. Those values are going to take off and grow. Whereas if I am looking at a function that has a base between 0 and 1, if b is between 0 and 1, then that's exponential decay. Think about 1/2. If I have 1, I cut that in half, I have 1/2. I cut that in half, I have a quarter. Cut that in half, I have an eighth. Cut that in half, I have a 16th. So that is exponential decay. That's going to get exponentially less and less and less. In some exponential functions, especially those that model real-world situations, looking at the base alone can be a misinterpretation of the model. And here's an example of this. We have the function r of h with a base of 2.4, but our exponent is negative. Well, if I were to go ahead and to rewrite this as 1 over 2.4, you can see here that this value is less than 1. It's between 0 and 1, making this an exponential decay function. So let's go ahead and look at these examples and practice this. We want to go ahead and identify each function as exponential growth or decay and identify the base. So here's our first example. F of x equals 4 times the base 1/2 to the power of negative x plus 4 minus 2. I'm going to go ahead and I am going to rewrite this. Here we have an a value of 4. And this base, I want to go ahead and rewrite this with a negative exponent. I need to factor this out. Now, I want to have parentheses around my x minus h value. So if you don't see parentheses, you have to factor out that negative coefficient. So I have that there, okay? And then we have our k value back here. So now that I've factored out that negative, I can go ahead and rewrite this as base 2. This is base 2 to the power of x minus h, which in this case is 4 minus 2, which is our k value. Now, I color-coded there just to help us see where we're going, but in this example, our base is 2. The base is 2. What does this mean? This means exponential growth. And that's because the base is greater than 1. exponential growth because the base is greater than 1. Okay, let's go ahead and look at the next example. Here we have 7 times 1/2 to the power of x minus 6. Again, I have a value, which is 1/2. That would cause vertical stretch by a factor of 7. I don't have anything going on in my exponent, which makes things simple. And then I have a minus 6 back here. Our base in this example is 1/2. Here, base is 1/2. What does that mean? That means exponential decay because it is between 0 and 1. Here's our third example. We have 10 to the power of negative x. Our base really here is 1/10. If I go ahead and apply that negative exponent property, so now I have 1/10 to the power of x plus 5. There is your k value. Here the base is 1/10. That is exponential decay. Okay, so now that we've done that, we're going to go ahead and transition. Here is the first example that I'm going to go ahead and do with you. And they want us to identify the function as exponential growth or decay and then graph the function. So what we're going to do is we're going to look at the base. And right away you can see here that the base is 1/2. That means that this is exponential decay. Exponential decay. Now that we've identified that as base 1/2, what we want to do is we want to make this base 2 because we're going to graph using our key points from base 2. So this is really 2 to the power of negative 1 times x minus 3 plus 2. Okay, well, we're going to go back to our previous lessons, lesson 1 and 2 on graphing exponential growth and decay. We have here we have a c value. Well, first of all, I'll talk about my a value. A value is invisible. We have an invisible 1 up here in the front. It's not worth writing it because it's not doing anything. So, but don't get it mixed up. A is 1. The base is 2. So we're here with base 2. And our c value is a negative 1. That's going to cause horizontal reflection. We have an h value, which is a positive 3. We'll shift to the right. And our k value is 2. Okay, so what does this mean? Well, for graphing the horizontal asymptote, we need that. Y is equal to k, so that's 2. That comes from our k value. Next, our pseudo-origin. Our pseudo, if I can spell pseudo, pseudo-origin is h comma k. So in this case, it's 3 comma 2. So that's our pseudo-origin, and we'll graph our key points from there. So before I get to the key points, let's go ahead and place some axes on this. We are shifting, what, up 2. So I'm going to put my axis down here. Okay, and then my y-axis, since we have an h value 3, we're shifting to the right 3. I'm going to offset that. I'm going to move my axis kind of left 3 so that my function is centered. So there's our axes. Okay, let's plot the horizontal asymptote at 2. Okay, and then our pseudo-origin, I'll go ahead and plot that, which is right there. Okay, so there's our pseudo-origin. We're going to go ahead and graph the rest of the key points from that location, and I'll go ahead and put this down here. So we have our key points, which are x values, and then our y values are 2 to the x. And they were this: negative 1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. Now, I do affect these values based upon A and C. If you have an A value, you're going to multiply your Y's by A, right? That makes sense. Your Y values get vertical stretch or they reflect. And then your X values get affected by the C value. So I have C times your X values. So here, our C value is -1. So all of the sign values on all of these X values are going to change. And if you think about this conceptually, instead of going left, you're going to go right. And instead of going right, you're going to go left. And that makes it exponential decay, right? Base 2 is going to grow like this. Well, base 1/2 is the opposite. Okay? So let's go ahead and plot these key points from our pseudo origin. I'll start with my first one, and I'll put these points in blue. I'm going to go, instead of left 1 and up 1/2, I'm going to go right 1, up 1/2. So there's that point. 0, 1, this point is unaffected by the horizontal reflection. Instead of going right 1, up 2, I'm going to go left 1, up 2. And then once you have the kind of the direction, it's very, very easy. I'm going to go left 2, up 4, and then left 1, 2, 3, up 8. 1, 2, 3, 4, 5, 6. 4, 5, 6, 7, 8, 9, 10. Okay, so there's our key points. And now we're going to graph a smooth curve through these points. Okay, arrows on both ends, and ta-da, there is your exponential decay function. Now, do we have zeros or intercepts? Notice here in this case, we do not have a 0. I never crossed the x-axis. Y-intercept I do have. That was one of our key points. That was 0, 10. And we just kind of naturally came across that value. So you can see that here. So 0, 10. All right. It's important to note, sometimes you do have y-intercepts. Sorry, always. You always have your y-intercept because your domain is -infinity to +infinity. Sometimes you will have a 0. It just depends. Where's your asymptote? Where are you shifted? And do you have any reflections? Okay, here is a practice problem. I would like you to go ahead, pause the video, and I want you to try this example here. Remember, first identify, is it growth or decay? And then identify your transformational parameters, graph it, and then state the 0 and intercept if possible. Okay, go ahead, pause this one and try this. All right, hopefully you went ahead and tried this. This is exponential growth, because our base is 2. The base is 2. But we do have an A value of -1. This is an A value of -1. That causes our function to go down instead of growing up. Okay? We had a H value of +4. That gives us our horizontal asymptote here at +4. And we just used those key points from what I call the pseudo-origin. So our pseudo-origin would be 0, 4 right here. And I just graphed the rest of the other points from that location. Okay, so there is the graph. Our y-intercept, that was one of the key points, 0, 3, and we did intersect the x-axis in this location at 2. Okay, here is another example. So please write down this example, where again we're asked to state if it's exponential growth or decay, and then graph it, and then state the 0 and intercept. This example, I really want to stress the importance of looking at the exponent. And do you see how there's a negative coefficient in front of x? But it's not in factored form. I don't have parentheses around my x minus h factored. So what I want to do is I want to go ahead and factor out this negative, which again, this is our c value. So negative c, x, and then the sign changes and it reveals our true h, which is not a +4, but it's a -4, because remember, h always switches signs. And then our k value, which is negative 1. So, looking at this, I'm going to leave it like this, but looking at this function, notice how we have 2 to the power of negative 1. This is base 1 half. Base 1 half. So this is exponential decay. Exponential decay. Because 2 to the power of negative 1, that is 1 half. Now I'm going to leave it in base 2 because I want to graph it with the base 2 key points. I do have a C value of negative 1, like I said. H is negative 4. And our horizontal asymptote comes from the K value, which is negative 1. So the horizontal asymptote y equals negative 1. The origin that we're going to use, PO, I'll abbreviate it, is H comma K, negative 4, negative 1. Okay? And then let's go ahead and graph. So I'm going to set my axes. I do have horizontal reflection here, and I'm shifted down 1. So let's go ahead. We'll put our axis here, down here. And we do have to go left 4, so I'm going to shift my axis right 4. Okay. All right, and then our horizontal asymptote is at negative 1, so we're down here. And the pseudo origin is on that line, so negative 4, 1, 2, 3, 4, down 1. So we're here. Okay, there is our function, and what we want to do now is graph with the key points. So you don't have to make the table. If you know the key points by heart, you can go ahead and just plot them, but I'd like to jot down these key points just in case students forget. Okay, so there's our key points, and we do have a C value, which is negative 1. So I need to multiply by the C value, which is negative 1. Now, think about what's going on. We have a horizontal reflection. So what's going to happen is I'm going to go the opposite direction. Okay, so let me plot these points. So my first one, negative 1, 1 half. So left 1, up a half. Well, instead of going left, I have to horizontally reflect. So I'm going to go right. That point would be here. 0, 1. Well, there is my 0. That looks like it's at negative 5. Okay. That is not affected by the C value. 1, 2. So normally I would go right 1, up 2, but I have to reflect. I'm going left instead of right. So left 1, up 2. Left 2, up 4. And left 1, 2, 3, up 8. 1, 2, 3, 4. Right there. Okay. And so here is our graph. And I'll draw a smooth curve through these points. And we're going to flatten out towards our asymptote in this direction. There we have it. Okay. And notice one of my key points is not the y-intercept. So down here, I need to go ahead and find the y-intercept, and we do that by evaluating the function at 0. So the x value for an intercept is always 0. So what is g of 0? So that gives me 2 to the power of negative 0 plus 4 minus 1. So we get 2 to the power of negative 4 minus 1, which is 1 over 2 to the 4th minus 1, which gives us 1/16 minus 1, giving us negative 15 over 16. So that's going to be the intercept, 0, negative 15 over 16. Students often ask, hey, can I go ahead and generate a decimal for that? Sure, but you don't have to. There's nothing wrong with negative 15 over 16. All right, here is the last example. Please go ahead. I want you to try this example. Do not be thrown off by the base 0.5. 0.5, that's 50 cents. What is that? Isn't that 1/2? 1/2, 0.5, that's 1/2. Okay, so don't be scared by that. All right, go ahead, pause me, and then we'll check the solutions here in a moment. All right, here is the solution. We went ahead and we had a c value of -1, so we can just make that base 2. 2 to the power of x minus 2. This is exponential growth, and we're just shifted to the right 2. So we have a standard normal graph, just shifted to the right 2, and that is it. We do have a y-intercept at 1/4. If you went ahead and just divided by 2 one more time going this direction, you would get 1/4, or you could plug in 0 as done here. And then we have a horizontal asymptote at y equals 0, so there is no 0. No 0 there. All right, a couple of critical thinking questions to close out this lesson. Will a function, exponential function, always have a y-intercept? Explain. Will an exponential function have a 0? When will it not have a 0? Give an example as part of your explanation. Go ahead, pause video, try that, and then I'll show you the closure results here in a second. All right, here is the solution. Yes, exponential functions will always have a y-intercept. That's because their domain is all real numbers, from -infinity to +infinity. Will an exponential function not have a 0? Well, if we have a horizontal asymptote that's shifted up, that will not go ahead and have a 0. So 2 to the power of x plus 5, that has a horizontal asymptote at 5 and it's exponential growth, not going to have one. Also too, what if we are shifted down, but we have a vertical reflection? Okay, and an example of that would be g of x equals negative, I'll say, 2 to the power of x minus 2. So we shift down, but we reflect the other direction. Not going to have a 0. All right, hopefully in this video you learned how to identify exponential growth and decay, and we had a little bit of a refresher on graphing those functions. Like and subscribe. I'll catch you guys in the next video. See ya.